This section is all about integrating standard functions that you saw in the previous section, but we're going to make it a little bit harder because in the previous section you were just integrating, for example, cos of x. Now in this section we're going to make it harder because we're going to integrate cos of some function of x. So in part A, the function of x is 2x plus 3. So if we just had cos of x, we would know that that would integrate to sine of x. And that's because we can remember this diagram, and to integrate, we move up this diagram. So before we look at the method which we're going to use, just a bit of a word of warning. You might think that the integral of cos of 2x plus 3, because the integral of cos x is sine, is just sine of 2x plus 3. But we know this is incorrect because if you differentiate sine of 2x plus 3, because differentiation is the opposite of integration, you should end up with cos of 2x plus 3. But if you use the chain rule to differentiate sine of 2x plus 3, you would actually get 2 cos of 2x plus 3. So we know that our integral isn't just sine of 2x plus 3. So the only thing that we know how to integrate is cos of x is sine of x. We're going to look at two methods of integrating this. One method is called substitution, and the other method is going to be by inspection, using the fact that integration and differentiation are opposites. So the first method that we're going to look at is substitution. So the way substitution works is we're going to say to ourselves, well, if we had cos of just a single variable, then we would know how to integrate that. So what we're going to do is we're going to create a new variable, which is our substitution. So we normally use the letter u for that substitution, and we're going to let u be the inside function of x. So in this case, it's 2x plus 3. The reason why that helps us is because our integral then becomes the integral of cos u, which is simpler than 2x plus 3. And we've still got dx on the end. All we've done is replace 2x plus 3 with u. Now the problem with this is dx tells us that we want to integrate with respect to x, but our integral is in terms of u. So they don't match up and we can't do that at the moment. So with this method, what we're going to do is we're going to try and make dx into du. We're going to replace dx with du. And in order to do that, we need an equation with both dx in it and du in it. So that equation we're going to get by differentiating u with respect to x. So we're going to find du by dx, which is 2. So the next line of working out that I'm going to do isn't really great maths because du by dx isn't actually a fraction. But it turns out that you can treat it like a fraction. So we don't need to worry too much about why it's not a fraction. Let's rearrange du by dx equals 2 to get dx the subject. So if we rearrange that, we're going to get dx equals a half du. The reason why we've done that is because now we can replace dx with something to do with u. So we're going to have cos u, and then dx is a half du. So we've achieved our aim. Now we've eliminated x, and we've just got an integral where everything is in terms of u. So you don't need to, but you can take the half as a factor out of the integral. So we're going to have half integral of cos u du. So we know how to integrate cos of u with respect to u. That's just sine of u. So we're going to have half sine of u plus our constant of integration. And then our last step is to go back to x. We've invented u to try and help us solve the problem. Our original problem didn't have u in it. So our answer should just have x's in it. So all we're going to do is replace u with 2x plus 3. So our final answer is going to be a half sine of 2x plus 3 plus our constant of integration. It's always a good idea to check that you've done it right. If you differentiate this using the chain rule, then you should end up back at our original function that we were integrating, which we do. Another method that you could use would be to just do it by inspection. So the way by inspection works is we're basically asking ourselves what function differentiates to cos of 2x plus 3. because we know that when we integrate cos of 2x plus 3, we're going to end up with some function that we're trying to find. And we know that differentiation is the opposite of integration. So if we differentiate our answer, we should end up back at cos of 2x plus 3. So we know that it's going to have sine of 2x plus 3 in it, because when you differentiate sine, you get cos. The problem is, if you use the chain rule and worked out what is the derivative of sine of 2x plus 3, you'd actually get 2 cos of 2x plus 3. So we need to put a half here to ensure that we end up back at cos of 2x plus 3. And then in B, let's use the method of substitution again. So here, our inside function is 4x plus 1. So we're going to let u be 4x plus 1. And the reason why that helps us is because then our integral is just e to the u. And we know how to integrate e to the u. The problem is we've got dx on the end and we want du. So we're going to have to work out du by dx. Du by dx in this case is 4. And then we're going to rearrange this to get dx the subject. So dx is equal to a quarter du. The reason why we've done that is because now we can replace dx with a quarter du, and our integral is just in terms of u. So you don't need to, but you can take a quarter as a factor out of the integral, and we're just going to end up with the integral of e to the u with respect to u. So we know how to do this. We've already seen in the previous section that if you integrate e to the u, then you're going to get e to the u. And then don't forget your plus constant of integration. Now we just need to go back to x because we want our answer to be in terms of x and not u. So u is actually equal to 4x plus 1. And then it's a good idea to check this. If you differentiate this function using the chain rule, then you will end up with e to the 4x plus 1, which is what we wanted.